Okay, today we will be looking at the third tutorial of CRE. The topic will be on kinetics of homogeneous reactions. So let us look at the first question. A certain first order reactions has a rate constant of 0.175 seconds at 20 degrees Celsius. So this is a first order reactions. A rate constant of this. So this is K. Rate constant K at 20 degrees Celsius. Calculate the value of rate constant at 60 degrees Celsius if the value of activation energy is E is 55.5 kilojoule per mole and 121 kilojoule per mole. Comment on the impact of activation energy on temperature dependence of rate constant. So we look at here, this question, you can see that it's got to do with calculating we are going to evaluate the effect of temperature on the rate constant K. So for this, we have to use the Arrhenius equation of K is AE negative E over RT. So this is the primary equations that we are looking at. So let us look at question part A. So there are actually two ways of solving it. They may look different, but actually essentially the mathematical operations, they are actually very similar. So I will show you two ways and you can see that which way you are comfortable in it when it comes to solving this in your assessment. So part A, what I will do is I will solve for the value of A first, given based on the information given by the questions. Okay, so there is a K is 0.175 per second. So A is the unknown that we are going to solve. E to the power of E. This E is the activation energy and is given for part A is 55.5 kilojoule per mole. But do take note when you solve this question because this is given in kilojoule per mole. So we would convert it into SI unit so as to avoid any confusion. So the SI unit will be in joule per mole. So this is 55500 joule per mole and divided by RT. So R is ideal gas constant of 8.314 multiplied by the temperature of 20 degrees Celsius and is in Kelvin, it will be plus 273 Kelvin. So for this, we can actually simplify by using a calculator and you get a value of 1.275 times 10 to the power minus 10 A, and A will have the value of 1.373 times 10 to the power of 9. Then the unit will be per second because the exponent, this part is dimensionless. So, and K has a unit of per second. So therefore your A must also have a unit of per second. So with this A, we can actually use it to solve for the value of rate constant K at the other temperature of 60 degrees Celsius. So at 60 degrees Celsius or 60 plus 273, which is 333 Kelvin absolute temperature. Your K will be, I just rewrite the Arrhenius equation, AE to the power negative E over RT, and we are going to solve for this K over here. This is K2 at temperature T2. So K2 will be, A is, we have solved from question 1, 1.373 times 10 to the power 9 multiplied by E negative. So this E is your activation energy again. Make sure we use the one in joule per mole. Divide 8.314 multiplied by 333 Kelvin. So with this, you can see that it's actually a very simple question because all you need to do is just to use a calculator and work out the value of K2, and you should get the value of 2.701 per second. Okay? So let's look at part B. The questions here again says that essentially the question is the same, just that we are changing E. Now I'm going to show you a different way of solving this question. We start with the Arrhenius equation again. K is AE to the power E over RT, negative E over RT, and K1 is actually the K that they're given to you. So I just term it as K1, which is A e to the power negative E over RT1, because the rest are constant. Activation energy, ideal gas constant, and this frequency factor, they are all constant. So the only two variables is your temperature and your K. After all, we are actually solving questions pertaining to the effect of temperature on the rate constant K. So we will write K2 is AE to the power negative E over RT2. And if we take 2 divided by 1, so you get K2 over K1, and the 2, you will see the A will be divided by A, and E to the power negative RT2 divided by E to the power of negative E over RT1. So this will be cancelled off into unity, which is 1. And from here, we see that we can actually apply the law of indices, where the base is the same. Just take the two powers, subtract each other because of the divide. So you should get E to the power negative E over R, 1 over T2 minus 1 over T1. Okay? And of course, this is K2, K1. So we are going to solve for K2. We can move the K1 to the other side. Okay? And from here we can see K1 is given at 0.175. So we just sub in the value 0.175. E is just a base, negative. Now for question part B, do note that we are using a different activation energy of 121 kilojoule. So again, it's 121 kilojoule. We have to convert into joule per mole. So we just multiply by 1000. And R is 8.314, our ideal gas constant. And the two temperature we are working at is 333. And T1 is the temperature at 20 plus 273. You get a 293. So from here we can see all we need to do from here is just use our calculator and solve this whole complicated equation, but essentially they are all numerical. So for this, if you solve, you should get the value of 68.28 per second. Alright. Now we're going to answer the last part of the question. Comment on the impact of activation energy on temperature dependence of rate constant. So what I did was we can actually draw a table, value of K2. Okay, this side I place activation energy. This one I put as temperature. So at 20 degrees Celsius comparing to 60 degrees Celsius. So the activation energy of 55.5 kilojoule per mole. And this one is 121.0 kilojoule per mole. So at 20 degrees Celsius, the question state that they have both of them have the same rate constant of 0.175. Right? So after our calculation, for part A, we get 2.701. And part B, we have 68.28. So from here we can see that at a lower activation energy, an increase of 40 degrees Celsius increases the value of K2 by around close to 20 times. But however, at a higher activation energy, the change in temperature, the change in the rate constant has a magnitude of close to around 60 times. So from this we can say that high activation energy reactions is more sensitive to temperature change.